Okay, class, today we are going to continue with chapter 4 and we're going to continue on. Today we're going to talk about exponential functions. Okay, and so this is what we're going to cover today. So let's start with exponents and properties. So this is a review of what we did at the beginning of the semester. Let me see here. Okay, so we call the definition of a to the m divided by nth power. Okay, so if a is a real number, m is an integer, and n is a positive integer, and we know that we wanted a to the nth root of a is going to be a real number, then we can define a to the power of m divided by n can be rewritten as an nth root raised to the nth power. So for example, we can look at 16 to the 3/4, and so we can rewrite this as the fourth root of 16 raised to the third power. And so that would give us the fourth root of 16 is 2, and then 2 to the third is 8, and so we can solve these. Also, if we have a negative exponent, then we can use the rule that gives us the reciprocal, right? So it's 1 over 27 to the 1/3 power, and then we can apply that definition, and we could use this as the third root of 27, which is 3, so we get 1/3. And then finally we get 64 to the negative 1/2, which is 1 over the square root of square root of 64, which gives us 1/8. And so we can use this to solve certain things. Now, in this section, we extend the definition of a to the r to include all real, not just rational values of the exponent r. Okay, so for example, 2 to the negative third power. So we can look at that. Might be evaluated by approximating the exponent of the square root of 3. Okay, so with the rational numbers 1.7, 1.73, or 1.732, depending on how many decimal places we want to go. Okay, so we can estimate this, and so that means we can estimate 2 to the power of square root of 3. Now, because these values approach the value of the square root of 3 more and more closely, it seems reasonable that 2 to the square root of 3 should be approximated more and more closely by the numbers given here, and so on. So the closer that this number gets to the square root of 3, the closer the 2 to the square root of 3 will be closer to the correct answer. I mean, that should be intuitive. Now, these expressions can be evaluated using rational exponents as follows. So 2 to the 1/7 power is the same as 2 to the 17th over 10, right? And so then we can use the rule to say, okay, the 10th root of 2 raised to the 17th power, and that gives us approximately 3.249, and so on. Okay, so we can approximate this using our techniques. Okay, now to show that this assumption is reasonable, see the graphs of this function 2 to the x. Okay, so with 3 different domains. So here's integer domains, right? So where x just takes on integer, and here's where it takes on the selected rational numbers. Okay, and then here's where we use all real numbers, and it becomes a smooth curve. So obviously, if we include all real numbers, this curve includes a smooth curve, or creates a smooth curve. And so if x is equal to 1/3, or excuse me, the square root of 3, then it should give us a value that's exactly equal to 2 to the square root of 3. So using this interpretation of real exponents, all rules and theorems of exponents are going to be valid, and all real number exponents, not just the rational ones. So in addition to the rules of exponents presented earlier in the review section, we're going to use several new properties that we're going to see in this chapter. So here's some additional properties that we're going to use. So for any real number a greater than 0 and not equal to 1, the following statements are true. A to the x is a unique real number for all real numbers x. Okay. Also, a to the b equals a to the c if and only if the exponents are also equal. If a is greater than 1 and m is less than n, then a to the m is less than a to the n. But if a is between 0 and 1 and m is less than n, then a to the m is going to be greater than a to the n. Okay, so properties a through a and b require that a has to be greater than or equal to greater than 0, so that a to the x is always defined. Okay, for example, negative 6 to the x is not a real number if x is 1/2, right? Because you can't take the square root of a negative number. This means that a to the x will always be positive. Okay, since a must be positive, in property a cannot equal 1 because 1 to the x equals 1. Okay, which means that we don't have an exponential curve, and that means it's going to be 1 for every real number, and so it just leads to a constant function. Okay, for property b to hold, a must not equal 1 since, for example, 1 to the 4th equals 1 to the 5th. So even though 4 is not equal to 5, they're still the same. So again, this only applies to values of a that are not equal to 1. Okay, so if we go back to here, for a and b, this is what we mean. Okay, so a is a unique real number, so a to the x. So obviously we don't want a to be 1 here, and we don't want a to be 1 here. Okay. Properties C and D say that when a is greater than 1, increasing the exponent on a leads to a greater number, but when a is between 0 and 1, increasing the exponent leads to a lesser number. Okay, so when we talk about a, we're talking about the base. Right here. So we're talking about the base here. Okay, so if the base is greater than 1, then increasing the exponent here, if a is bigger than n, or excuse me, if n is less than n, then if a is bigger than 1, then this inequality holds. If a is less than 1 but bigger than 0, then, and we have the same thing, m is less than n, then it flips the inequality because as we increase the exponent, the a actually gets bigger here when m is smaller. Okay? So if f of x equals 2 to the x, so here's our exponential function, find each of the following. So f of negative 1. So if we stick in negative 1 for x, we get 2 to the negative 1, which is 1/2. Okay? If we want f to the 3, then we just put x equal to 3 here, and then it would be 2 to the 3rd power, which is going to be 8. And likewise, if we have 5/2, then we're going to raise 2 to the 5/2 by substituting 5/2 in for x, and we get 2 to the 5/2, which is going to be what? Well, the thing we're going to do is raise this to the power of 5 first, so that would make 2 to the 5th, right? 2 to the 5/2 power, right? Well, 2 to the 5/2 power is 2 to the 5th to the 1/2 power. We can split that up using the power rule or power property, right? And then 32, right? 2 to the 5th of 32. The square root of 32 is, well, we split this into two parts, two factors. So we can write this as the square root of 16 times the square root of 2. Well, the square root of 16 is 4, and so we get 4 times the square root of 2. Okay, what about this one? 2 to the power of 4.92. Well, we can use our calculator for this one. Okay. Now, an exponential function, if a is greater than 0 and not equal to 1, then exponential function with base a is given by this formula. So this represents an exponential function. So notice it has a base a and an exponential of a variable x. Now note, we do not allow it to be 1 for the base because then it's not an exponential function. If a is equal to 1, then it just becomes f of x equal to 1, which again is not an exponential function. Now we repeat the final graph with real numbers as the domain and summarize important details here. So now here's some important details that we're going to want to keep in mind. The y-intercept is always going to be 0, 1. Okay? Because 2 to the x is greater than 0, for all x and 2 to the x approaches 0, as x approaches negative infinity, the x-axis is a horizontal asymptote. Okay? And as the graph suggests, the domain of the function is all real numbers, and the range is going to be all positive or all non-negative values for the range. Okay? Or excuse me, it's going to be all positive numbers because 0 is not included. So, and the function is an increasing, right? So you can tell from the graph it's an increasing function on the entire domain and therefore is a one-to-one function. Okay, so exponential functions, again, have this form: domain, all real numbers; range, all non-real numbers for the range. And of course, for this particular exponential function, 2 to the x, it looks like this. So notice that it always goes through 0, 1, and it also goes through -1, comma 1/2, right? 1 over 2, and then also 1, comma 2. Okay, so notice that it goes through -1, comma 1 over a, and this is 1, comma a. So these 3 points are always going to be the same. 0, 1, -1, comma 1 divided by a, and then 1, comma 2, or 1, comma a, the base. Okay, and we got the x-axis is the horizontal asymptote as x approaches negative infinity. Okay, and those are the 3 points. So these are the 3 points that you want to remember. So these are characteristic of any exponential function of this basic form. Okay? And this is what if, in this case, what if x is negative? Or excuse me, a is less than 1. What if a is between 0 and 1? Now it's a decreasing function, right? So this makes sense based on what we were talking about before, right? So if a is between 0 and 1, then we get a decreasing exponential function. Okay, and notice these values here too. So again, it's of the form a to the x. A is between 0 and 1, decreasing and continuous on the entire domain, right? So the domain is all real numbers. The range, again, is all non-negative numbers. And the x-axis is still the horizontal asymptote as x approaches positive infinity. Okay, so also notice here that it goes through these 3 points. Okay, so again, it goes through, notice it's flipped. This is flipped, so it goes through, still goes through 0, 1. So that's the same, but notice it goes through -1, comma 1 over a, and then 1, comma a. Okay, so if you notice here, goes through here. Oh, hold on a second. Oh, this didn't change. No. This is wrong. These are typos. These are typos. It should be 1. It should be -1, comma a, 0, comma 1, and this should be 1, comma 1 over a. It should be flipped. Oh, wait a minute. Hold on a second. There's something different here. No. Okay, never mind. Never mind. It is the same. I keep forgetting. This is less than 1. Okay, never mind. Sorry about that. Keep remembering. This is 1/2. So we're under the impression this is between 0 and 1. So it's still the same. So the same 3, but this is 1/2. So that, yes, yeah, that makes sense now. So it's 1 comma a, negative 1 comma 1 over a, and 0, 1. So these 3 points are still the same, even though we're between 0 and 1. Okay? Okay, so notice these are flipped, so understand the differences. This is where a is between 0 and 1, so it's a decreasing function. This is when a is greater than 1. Okay? So also, remember the graph of y equals f of negative x is the graph of y equals f of x reflected across the y-axis. Okay, so notice that this is the same as this, but reflected across the y-axis. Thus, we have the following, that if f of x equals 2 to the x, then f of negative x also is the reflected of that, right? So that gives us the 1/2, right? Because 2 to the negative 1 gives us 1/2. So this is the reflection of this across the y-axis. Okay, and of course, if you look at the graphs, it's obvious from the graph that you're pivoting this around the y-axis right there on that pivot point, 0, 1. Okay, now the graph of f of x 2 to the x is typical of all graphs of a to the x, where a is greater than 1. Okay, for larger values of a, the graph just becomes steeper and steeper and steeper because it is being stretched upward. Okay, so it actually gets steeper. Okay, but it has the same general shape. If it's between 0 and 1, if the base is between 0 and 1, then you're going to get this function. And again, as this 2 gets bigger and bigger and bigger, well, this whole thing gets smaller and smaller and smaller. And so you get this type of behavior. So as the base gets bigger here, it gets more and more stretched upward, right? Like a vertical stretch. And here, as the base here gets smaller and smaller and smaller, in other words, this denominator gets bigger and bigger and bigger, it does the same thing, okay? Because, again, this is a reflection. So it should make sense now that if I have this, then I'm going to get the reflection of 1/10 to the x power is going to be the reflection of this one, okay? So just this gives you an idea of how the characteristics or the behaviors of an exponential curve looks like. So here we go. So 1, the points negative 1 comma 1 over a, 0 comma 1, and 1 comma a are on the graph. These are always on the graph. So you can automatically graph these and sketch the graph knowing these 3 points. If a is greater than 1, then f is an increasing function. If a is between 0 and 1, then f is a decreasing function. The x-axis is going to be a horizontal asymptote, and the domain is going to be all real numbers, and the range is going to be all non-negative numbers. So if you know these characteristics here, then you can sketch the graph and then use transformation if necessary to sketch other exponential curves. So if we want to graph this curve and give the domain and the range, we can do so. We know the x-intercept is going to be at 0, 1. There's also going to be a point at what? There's going to be another point at what? Negative 1 comma what? 1 over a and 1 comma a, right? So we know that this is going to go through 0, 1, but it's also going to go through negative 1 comma 1/5, or excuse me, negative 1 comma, hold on a second. Yeah, no, negative 1. Yeah, negative 1 comma 5. Yep, because it's going to be 1 over a, which is going to be 1 over 1/5, which is 5. So it'll go through negative 1 comma 5. Okay, and then it's also going to go through 1 comma 1/5. So it'll go through those 3 points. Okay, we also know that the x-axis is the horizontal asymptote, and the domain is going to be all real numbers, and of course the range is going to be all non-negative real numbers, and it is 1 to 1, and it's also a decreasing. Hold on a second. The function is increasing? No, this is a decreasing. That's a mistake. This is decreasing on the entire number line. Decreasing. This is between 0 and 1. So this is a decreasing function, not an increasing function. And there we go. So we got the plot. So we plotted negative 1 comma 5, 0, 1, and 1 comma 1/5. And so now we know it's going to go something like this. Okay, graph the function. So here we go. So we got negative 2 to the x. So this is going to be negative outside the power. So this is a reflection. So this is going to be reflected down across the x-axis. Okay, so if you think about it, it's going to be the same graph reflected across the x-axis. So this means that the domain is now still going to be all real numbers, but now it's going to be all negative real numbers for the range. Okay, because now it's reflected down to the bottom or down below the x-axis. Okay, so here's our basic function. Now using transformations, we know that it's a reflection, so this is going to be reflected down, so it's going to go through 0, 1, right? It's going to go through 1, 2, and it's going to go through negative 1, 1/2, negative 1/2, or 1/2. So now if we flip it down, it's going to go through negative 1, negative 1/2, 0 comma negative 1, and 1 comma negative 2. Okay. Now here we go. Now look at this. Now what's going on? Well, now we're adding 3. Now are we inside or outside the function? In this case, we're inside the function. We're adding 3 to x. So that means this is going to be a horizontal shift to the left, 3 units. So now all we have to do is sketch 2 to the x and then move it to the left 3 units. And we can do that because we know those 3 points, right? So we know 2 to the x is going to go through what? Negative 1 comma 1/2, 0 comma 1, and 1 comma 2. Okay. Now if we move all 3 of those points to the left 3 units, that means the 1 comma 1/2 is now going to become what? It's going to become what? 3 units to the left means that the 1, or the negative 1, is now going to become negative 4. The 0, 1 is now going to become 3, 1. And the 1 comma 2 is now going to become 2 comma 2. And again, the domain and the range are still going to be the same. The horizontal asymptote is still going to be the x-axis. Okay? And so notice how the points move over. So 0, 1 becomes negative 3, 1, and so on. Okay, now we're going to add one more thing. So now we're subtracting 2 from x, and then we're subtracting 1 from outside the function. So this is going to be a vertical shift down 1 unit. So now again, we're going to start with our basic function of 2 to the x, and then once we sketch that, then we're going to move it 2 units to the right and 1 unit down. Okay. Notice that also if we're going to move it down, the asymptote is going to go down 1. So the asymptote, the horizontal asymptote, is going to move from the x-axis to y equals negative 1. And so that's going to change the range. So the domain is still going to be the same, but the range is now going to go from, the range is -1 to infinity, okay? Because the horizontal asymptote was moved down 1. And so this is what it looks like. Okay, so here's our horizontal asymptote at y equals -1. So our 0, 1 went 2 units to the right, 1 unit down to 2, -0. Okay, and again, as long as you have those 3 points, right, so this would be 0, 1, -1.5, 1, comma 2. Okay, we can use those 3 points and then move those 3 points 2 units to the right, 1 unit down. Okay, now solve an exponential equation. So now what we're going to do is we've got to match this with this. Okay, so we've got to figure out a way to solve these, right? And so one way is to write this, if it's possible, write this as with a base of 1/3. Okay, but it's not always possible to do that. Okay. So solution, write each side of the equation using a common base. Okay, well, we've got a base of 1/3. How can we write this with a base of 1/3? Okay, well, we've got 81. Can we write that as a power of 3? And the answer is yes. Okay, because we know this is 9 squared, and 9 is 3 squared. So that means we could write this as 3 to the 4th power. Okay, but we want 1/3. So one way is to write this as 3 to the -4th power and then bring it in. Okay, so let's see how that looks. So here's our setup. So let's rewrite this as 3 to the -1. Okay, we could do that, right? Because 1/3 is the same as 3 to the -1 power, right? Okay, well, now we can bring in what we were just talking about and say, okay, this is the same as 3 to the 4th power, right? There we go. Okay, so we're going to use this here. Okay, so 81 equals 3 to the 4th power. So guess what? Now we've got bases that are the same, and 3 to the -x is equal to 3 to the 4th power. Now we're going to use the property that if the bases are the same and the two expressions are equal, then the exponents must be equal. So this works for exponential functions, right? So we got two exponential functions where the bases are the same and they're equal to each other, then that must mean that the exponents must be equal to each other. And so -x has to equal 4. And if we solve this, that means x has to equal -4. And we're done. We solved it. So the solution set of the original equation is just -4. So x equals -4 will work. Okay, let's do the same thing here. So again, we're going to do the same thing. We want to get the same base. So we've got 2, and we know we can write this as 2 to the 3rd, right? So let's see if we can do that. Okay, so there we go. We wrote it as 2 to the 3rd, but now we've got this, right? So we've got a power raised to the power, and so we can use our power rule to simplify this. Okay, so we get 3 times x minus 6, and then use a distributive property, we get 3x minus 18. And now we can use the property that we've got two exponential equations, or excuse me, two exponential functions that are equal to each other with the same base. That means the exponents have to be equal. And now we've got an equation we can solve for x. And so we can solve and get -2x equal to -22. We get x is equal to 11. Okay. Now, we could check by substituting at 11 back into our original equation, and sure enough, we'll get the same thing on both sides. Okay, so check by substituting 11 for x into the original equation, and we'll show that the solution set is just 11, or that x equals 11 is the solution. Okay, look at this one. So here we got x as the base, and we've got 4/3. Okay, so now, what are we going to do here? Well, we've got to do something to get rid of this 4/3 to get x to the 1. Well, how do we get x to the 1? Well, we can raise both sides to the same power, right? Well, what power would make this equal to 1? Well, the power property means that we have to multiply exponents. Well, what two exponents, if we multiply them, will give us 1? And that answer is the reciprocal. So what we're going to do is we're going to raise both sides to the 3/4 power. Okay? Okay, so what we did, so notice what we did. So we have it's raised to the 4th. So what did we do? We took the 4th root of both sides to get rid of that 4. And the 4th root is plus or minus 3. Okay? Now what we're going to do is we are going to raise both sides to the power of 3. And we get plus or minus 27. Okay? And so we get two answers. Okay? Now, why do we have the plus minus here? It's because we had to take an even root. And so anytime we take an even root, we got to make sure we have the plus minus here. Okay? Okay, so our solution set is plus or minus 27. Now, check that both solutions work in the final one, okay? In the original equation. Okay. An alternate method, which is the method I was starting with, is we can use another, right? So here we can raise both sides by 3/4, right? So we can raise it by the 3rd power, cube each side, right? We get x to the 4th, and then we can also take the 4th root of both sides. Okay, so more than one way to do this. So this time we cubed first, and then we took the 4th root. And we get the same answer. Okay. Now, compound interest. Now, recall that the formula for simple interest is I equals PRT, where P is the principal, or the amount deposited, or the amount loaned, or borrowed, I should say. R is the annual interest rate, expressed as a decimal. T is the time in years that the principal earns interest. And suppose that T is 1 year. Okay. Then, at the end of the year, the amount has grown by the principal plus the interest, right? Because it's 1, T is 1. So we get principal plus the interest, or P times 1 plus R. Okay, so this is for 1 year. If this balance earns interest at the same interest rate for another year, the balance at the end of that year will increase as follows. So it'll be this amount, right? Because this is the principal for at the end of the first year, this is the principal. So this is going to be the principal plus the principal times R, right? If we go 1 more year, right? So if we simplify it, then it becomes P times 1 plus R times 1 plus R, which gives us P times 1 plus R to the 2nd power. Interesting. Now if we go 1 more year, let's go and now this is our balance or principal at the end of the 2nd year. Well, what if we go 1 more year? Well, we see another pattern, right? We see a pattern going on. So if we do, this is the principal amount, so this is our new P. Then we go P times R, right? So I take our P times R, and now we simplify this. We get P times 1 plus R squared times 1 plus R. And it becomes P times 1 plus R cubed. And so if we continue this, we get a formula for interest that is compounded annually, right? So now we've got the amount that we have after t years. So we take a lump sum, and for an investment that's compounded annually with an annual interest rate of R over t years, this will give us our future value, or the achieved value. It's the future value, but it's called the oh my gosh, well, I'm having a brain fart, but we call it the future value. Okay, so now what if it's different than a year? Okay, so compound interest. So here's the general formula. If P is the number of dollars deposited in an account, so we're assuming a one-time deposit and we're letting it ride for a number of years, paying an annual interest rate of R as a decimal, compounded n times per year, okay? Then after t years, the account will contain A dollars, okay? So according to the following formula. So that means that if we take, so if it was annual interest rate, how much it would be compounded annually, n would be the number of compounds per year, so n would be 1, and we get the formula we were just using, okay? But what if it's compounded differently? What if it's compounded monthly? Okay, then n would be 12. Or if it was compounded quarterly, right, that would mean n would be 4 because it compounds 4 times a year. Or what if it's weekly compounding? Then it would be 52. Or if it was daily compounding, then you would have 365. Okay, see what I mean? And so the n, which is the number of compounds, changes depending on the problem. Okay, so here, suppose that you deposit $1,000 in an account paying 4% interest per year, compounded quarterly. Okay, so that's 4 times per year. Find the amount the account will have in 10 years. So now we're going to use the formula A equals P times 1 plus R over N to the Tn power. So this is a exponential formula, right? Exponential function or formula or expression, right? Here's the base, here's the exponent, and here's just some other constant. Okay, so R is going to be 0.04, N is 4, T is 10, and P is 1,000. And so all we have to do is plug and chug, right? And so when we put this in our calculator, we end up getting $1,488.86 rounded to the nearest penny. And so that is the amount that we will have in our account. So again, so we started with $1,000. We end up with $1,488.86. So the amount of interest that we earned over the 10 years is $488.86. Right? So we take the amount that it grew to minus the principal, and the rest is interest. Okay, so Becky must pay back a lump sum loan. She borrowed $6,000. She has to pay it back in 5 years. So what amount deposited today? Hold on a second. Becky must pay a lump sum. Oh, in 5 years. Okay. Okay, so she must pay a lump sum in 5 years, whatever this is. I don't know. But so let's say she owes this amount of money and it needs to be paid in 5 years. So what amount needs to be deposited today at a 3.1% interest rate compounded annually so that she has 6,000 in 5 years? Well, now we know this is her goal. This is what she needs to have. So this is the A, right? This is the future value. So we need to find P. What is the deposit amount, the principal amount? And R is 0.031 and T is 5. So the compound interest formula, again, now we're going to solve for P. We know everything else, so we're just going to plug and chug. Okay, so now we just solve for P, and we get P is approximately $5,150.60. So she's going to have that amount of money Now, in order to earn what? She'd have to deposit to earn basically what? $850, right? Approximately. So if Becky leaves the $5,150.60 in for 5 years in an account that pays 3.1% compounded annually, she will have $6,000 when she needs it. We say that 5150 is the present value of the 6,000 if interest of 3.1 is compounded annually for 5 years, okay? Or the principal amount. That was the beginning amount. Now, if only 5,000 is available to deposit now, what annual interest rate is necessary for her to get the 6,000? Okay, so what if she only has 5,000? Okay, what interest rate does she need to have in order to reach her goal? Now we know P, and we know A, and we know T. So now we just got to solve for R. So again, we're going to use the same formula, and now we're going to plug in everything except for R because that's what we're solving for. Okay, now we're going to divide both sides by 5,000, and then we're going to take the fifth root of that and then subtract 1. Okay, and when you put this in your calculator, you get approximately 0.0371 or 3.71% interest annually she needs to get, compounded annually. Now, the more often interest is compounded within a given time period, the more interest will be earned. Surprisingly, however, there is a limit on the amount of interest, no matter how often it's compounded. In fact, as you can see, if you do tables and you start increasing n, like as n gets bigger and bigger, the amount that you earn over the same time period goes up, but the amount that it goes up gets smaller. So it seems like it's heading towards a maximum. Okay. Suppose if we earn $1, let's use $1, and and we get 100% interest on it. Okay, so just to simplify things. Okay, so we deposit $1, and it's invested at 100% interest per year. Okay, compounded n times per year. So that means the interest rate is 1 as a decimal over n raised to the nth power, and we're doing this for 1 year. And p is equal to 1, so this is it. So what happens to this value a as n gets bigger and bigger and bigger? So as this value gets bigger and bigger and bigger. Note what happens. As n increases, look what's happening here. This is starting to get closer and closer to a particular number. In fact, this number is what we call the exponential, the natural exponential, e. Okay. In fact, this is the definition of e. As we take this to go to infinity, as n goes to infinity, this value approaches e by definition. So the definition of e, which is a real number, and it's not a variable. Okay. And this number appears many, many, many times in sciences, okay, in nature. And this gives us the idea, or this brings us to continuous compounding. Because as n gets bigger and bigger and bigger, as we take more and more compounding, it eventually will get to the point where we are continuously compounding and we have to use e. So if we are dealing with continuous compounding, then and p is equal to p dollars, again, same scenario, p dollars is deposited, so this is our principal, and r is the interest rate as a decimal compounded continuously for 2 years, then the amount of money, the future value that we will have, is given by this formula, a equals p e to the rt power. So suppose we have that $5,000 and we're depositing in an account paying 3% interest, compounded continuously for 5 years. What would be the total amount that we would have? Well, if we use our formula for continuous compounding and we plug in the values, then what do we get? We get approximately $5,809.17 is what we'll have. Okay. Now check that daily compounding would have produced a compound amount of only about 3 cents less. So there's not much difference between continuous compounding and daily compounding. But make sure you use the correct one, because even if you're off by a smidge on the exam, if you use the wrong formula, you're going to be wrong. So make sure you use the right formula and you round appropriately, usually to the nearest penny unless it says otherwise. Now, in example 7, we found that $1,000 invested at 4% quarterly over 10 years grew to this amount. Let's compare this if we did annually, right? Semi-annually, monthly, daily, and then continuously. So let's see how those amounts change. So we're going to use this compound formula for all of the compounding except for continuous. For continuous, we're going to use this. Okay? The results for the amounts of $1 and $1,000 are given in the following table. Okay? So here's the annual. We get this amount. Okay? Semi-annual, we get this amount. So it went up about $6, almost $6. Quarterly, there's our 86, so it went up another $1 or so, right? Or less than $1. And then monthly, it went up a little bit more. Okay? And then daily, it went up a little bit more. And notice that continuously, it only went up 3 cents. Okay? So the amount of increase is getting smaller and smaller and smaller. Okay? Now, comparing the results, we notice that the following. So compounding semi-annually rather than annually increases the value of the account by $5.71. Quarterly compounding grows to 2.91 more dollars than semi-annually. Okay? Daily compounding grew only by about 0.96 cents more than monthly compounding. Okay? And then continuous compounding grew by 3 more cents. So each increase in compounding frequency earns less and less additional interest. Okay? Now, exponential models. Okay? So exponential models are used for all kinds of things, not just for compound interest and finances and things like that, but also for growth models, decay models. All kinds of different situations come up. So the number e is important as the base of an exponential function in many practical applications. Okay, again, decay, radioactive decay, population growth, things like that. Okay, so the function here would be a exponential model. So we have our final value is equal to the initial value, the initial amount that we had, times this exponential piece, which is e to the k, where k is a growth constant and t is the number of years. Okay, or a decay constant if it's a decay. So let's take this example. We're going to use year and carbon dioxide. So here's the data that is indicating the years, and future amounts of carbon dioxide in the atmosphere may grow according to this table. May grow according to this table. Okay. So here's 1990, 2000, 2075, 2071, and so forth. So these are all future values here. So we've only got 2 data points. Okay, so again, this is not a very good, but let's assume that's using an exponential model. Okay, so these are made up data. Okay, so let's see what we get. So we make a scatter plot. So on our calculator, we make a scatter plot here, okay? And then once we see the scatter plot, then we can use our calculator to fit the best exponential graph, okay? And when you use the exponential regression part on your calculator, which is under your distributions, no, under tests, it'll be under stat, no, it's not, oh, where is it? It's under calc, I'm sorry. It's under stat calc. You're under your calc menu, and you're going to use the exp-reg for this. And what you can do is it'll give you this exponential. It'll actually give you your A value, and this is your B value. And so it'll give you the model, where this is only going to be good for this range value. Okay, and then what you could do is you could use the graph and the model to estimate when the future values of carbon dioxide will double, right? So, or triple over the pre-industrial level, okay, of 280 parts per million. Okay, so if you look at the graph, okay, shows that it is very close to the data points, right? That's what the regression does. It finds the best line through the data points, okay? That's also an exponential function. Okay, so now what we do is we graph double, right? 280 parts per million, that's what the starting point. We want to find where it's double. So what we're going to do is we're going to find out where the double is, and we're going to graph it as a horizontal line. So we're going to take y equals double this, or 560, and so that's going to be the red line. So if we plot this red line, and then we can find out where those two values intersect by using the intersection function under the second trace key, okay? And then once you find the trace key, then it'll tell you right there, okay, the intersection here, right here, 560, the intersection point right there is at 2864. So in the year 2864, or hold on a second, X is, let me see here. Let me just make sure. Yeah, so if you put the data, let me see. Yep, if you put the data years in, just like they are, yes, that is, oops, oh, hold on. Nope, hold on, sorry, I went too far. Okay, so 2864, is that right? 2064. 2064, and the triple, right, if it's triple, then it would be 3 times, right? 3 times 280, which is 840. So here you plot this line, and you can find the intersection point, and you find out that that's going to happen according to this model in 2130, or closer to 2131, or the end of 2130. Okay. Okay, and so that is the end of this section. So again, if you have any questions, please make sure you can do these on your own. Work these out. Make sure you can go through these and show. Now again, we're not going to be using graphing calculators, but you could practice using graphing calculators so you can understand what's going on, and it also would be helpful in other classes as well. But again, this is just showing you how technology can help you solve some of these stuff in real life applications. Okay, until then, have a great day, and I'll talk to you soon. Bye-bye.